today's topic is not immediately going to be connected to Tuesday's topic, and probably we won't see the connection today, but there is a connection, I promise. So we're going to go back to thinking about structure again in some sense. Remember that we had this in week 6. We introduced the category of pre-orders. So these were sets with an order relation on them, which is reflexive and transitive. And we said, I think we introduced this, well, I guess we didn't introduce this functor because then it would have been imported. But there is a functor that takes a pre-order and forgets about the fact that it's a pre-order and just gives you back the set, right? So on objects, it gives you the carrier. On functions, it gives you the underlying function. Because remember, the morphisms here have functions that preserve the order, so we can forget about the fact that you preserve the order. Gives, just the carrier, yeah, the underlying set, yeah. And then it's easy to show that if you forget about that the identity morphism is order preserving, you get identity. And if you forget about the composition of two morphisms are order preserving, then you get the composition of two morphisms, right? So that's not such a surprising functor, perhaps. But then we also had a more interesting functor which went the other way, which said that if you have a set, we were trying to figure out a canonical way to make it into an order, just out of thin air, right? And we said that there was one way to do it, which was to do the smallest possible amount of work, where we said that, well, if it's to be a pre-order, it has to be reflexive. So we better have that every element is related to itself. And that's all we had to do, right? So we put in the smallest order by saying that the order relation was given by equality, because that's reflexive. And equality is transitive, so you get that for free, more or less. So we have this construction, which for every set gives us a pre-order, and it plays nicely with functions. It gives order-preserving morphisms. But you could now ask more generally, what do you need to do in order to give a order-preserving morphism out of this thing into some other pre-order P, right? So we constructed this thing. We know that if P is another one of these, then we have the functorial action. So we know that just the function suffices. But more generally, you could say, okay, so I've constructed this thing. Now I might be interested in writing functions out of it or into it, right? So I would like to fill something in this hole such that I can turn every one of these into one of these. Right? Any ideas? Connor, do you have any thoughts?
Yeah, so let's see. We have to be order preserving. We're starting from an order that is exactly equality. So that suggests to me we're onto a good thing, because equality is one order, one relation that we cannot help but respect.
Yeah, so I've chosen the good direction here, right? Saying, what does it mean to make functions out of this thing? Well,
I think any old function from X into the carrier of P is going to preserve the smallest order.
Right, so you're saying that this should be enough. If we have a function from X into the carrier of P, we should be able to upgrade that into an order-preserving morphism from the smallest order into P. That's what
something of the sort, yes.
Okay, let's see. So I'll take such an F. Okay, and then here now, I have to give a monotone map from the smallest order into P, right? That's how we defined morphisms in pre-order. Okay, so I remember that I have to do two things for this. I have to give a function, and I have to prove that it's monotone, right? But the function, that's exactly the data that Connor told me I should have, right? So that's okay. And now here, I have to show that if I have x and y and they are equal, then f of x should be less than f of y. Right? Less than or equal to, yeah, importantly, yeah. So,
thank goodness for the or equal to, because we're going to need it.
Right. So I'm going to take x and y and some p And then I'm going to immediately pattern match on my P, which tells me I only have to consider the case where x is equal to y. So now the printing is annoying, but I need that f of x is less than or equal to f of x, which should follow from the fact that P is reflexive.
Looks good.
So I don't have to, but I just get pleasure from seeing that these two things line up perfectly. And then afterwards, I feel the need to delete it. Okay, so Connor's suggestion gave us one of these, but actually now I'm claiming that Connor is not such a bad egg because I'm claiming that every one of these actually comes from one of these. Let's see if we can prove this.
Yes.
So I'm going to do this.
Trying to avoid spoilers.
So I'm going to say that if I have all of this data, I'm now going to swap the order of these two. So if I instead start with such a thing, then I'm going to get such a thing. Okay, so I have my monotone map, and I need to make a function. But let's look at the underlying function of h. That's fun of h. Right? It has exactly this type. Right? So this was in some sense even easier. Okay, and now we could also prove that if we start here, go down, and then go back up again, we'd end up where we started, and vice versa, right? But let's save that for a little bit later. So the point is that in order to make one of these morphisms, you need to exactly do one of these. And now you could also notice that here I wrote it as a HOM in the category of preorders, but I could also write this as a HOM in the category of sets, right? So let me do that. This is a morphism in the category of set, which is a function from x to the carrier of p. But then I could also see that the carrier of p here, that's actually the action of this forgetful thing, right? So I could say this is act forget p.
You need the extra brackets there.
Here.
No, the ones.
No.
No.
Yeah. Yes. And similarly up here.
Yes.
Right.
And a bit of gratuitous extra alignment would be lovely.
Right.
You need an arrow.
I do need the arrow at the end. Yes. Okay.
X is up.
X lines up with
Line
the X.
P is up.
And the P lines with the P.
Awesome.
Right. And I suppose we could do something down here to make the point. Right. So we see that what we have is a way of flipping the smallest order here on the left to forget on the right and back again, right? So we could also do another example. So maybe you can be cameraman, Connor, if I go on the board. So let's think of another example, which is very different. So I'm trying to make a point that this is everywhere. So let's see that we have the rational numbers, so fractions, with, as it happens, its order relation. And we have the integers with its order relation. So these are things that I mean, 3.5, 3.555, etc., right? These are just 4, 5, 6, 7, and so on. So we could ask, are there any relation between these things and these things? Can anyone think of any? Jake has an idea.
So it's one way to it's backwards for the inclusion.
Right, so we can inject these here into here, right? Every integer has a representative as a fraction. So that's inject going this way. Okay, can we think of anything going the other way? I'll let Jake.
It's all preserving round up.
Right, so we can round up. Call this ceiling. And after we thought to round up, we could also round down, right? That's floor. And of course, there's other ways, there are other maps here. We could take our rational and then we could divide, then we could subtract 17 from it and then we could take the ceiling or something. But that seems less natural somehow, right?
I mean, if you add 17,
Yeah. But these seems to be the canonical ways to do it, right? Somehow just round up or round down. Okay, so now we could ask, what's the relationship between inject and say floor? Right, so let's say that I start here with some rational, q. Then I can round it down, floor. And I can now compare that with, so that's now an integer, right? So I can compare that with some integer I. The other thing I could do is I could inject the I and then compare that with q itself, right? And which way around is this? So I think if I round down, then q is going to be even greater than that. So if this is greater than this, if and only if this, I think, is that right? So let's say that the floor of q is greater than I, then q is going to be greater than the floor of q, which is greater than I, which is the same as inject of I. So if I have this, then I have this.
where those two greater equal different.
Yeah, so this is the one on integers, this is the one on rational numbers, right? And if q is greater than inject of I, so if q, for example, is 3.5, then if 3.5 is greater than I, then 3 is also going to be greater or equal to I, right? So we have an if and only if here. So again, we have this thing where we take a, maybe I should write it the other way around. So I like the order to be. So this is I less than or equal to floor of q. And this is inject of I less than or equal to q. Right. Inject of I, yes. This is floor of q. Okay, so we have this. And similarly, if I now, instead of looking at the floor, I look at the ceiling. So I say that the ceiling of q is less than or equal to I. And I can compare q with inject of I. And I think for the same kind of reason, if the ceiling is less than I, then q is also less than I because q is less than the ceiling. And if 3.5 is less than 4, then the ceiling of 3.5 is also going to be less than 4, right? You can't fail just because you round up because you're comparing with an integer to start with, right? So again, we see this thing where we are flipping an inject from the left to a floor on the right, or a ceiling on the left to an inject on the right, right? So it's kind of the same kind of thing as we saw with the other orders. So what we saw here on the screen was that we had, so the forget here is a little bit like the inject, right? It's the boring thing, that's obvious. And the smallest order, that's the interesting thing, which is the ceiling and the floor here, right? Yeah. So here we had the smallest order on the left. But here we saw that the boring thing was sometimes on the right and sometimes on the left, right? So we could ask again, well, can we think of something that would have the same relationship to forget, but is now on the right instead of on the left, right? So that would mean that we would come up with another map from pre-orders to sets, and we want to have this relationship, but I want to have the forget on the left and the other thing on the right, right? And in fact, Right, so that's the thing we talked about previously, the chaotic order, where we make everything related. So I'm saying that the carrier for the chaotic order on a given set B is B, and B and B prime are related if and only if true, right? So that's reflexive, transitive, and propositional. That was another thing we had. And if I now have a function from B to B prime, then that function is certainly going to preserve the order, because in the target I have everything related anyway, right? So now we can ask again, what does it mean this time to make an order preserving map into the chaotic order? Right? So now I flipped it, so I said put the chaotic on the right here, right? And for the reason I have said, this should also be really easy, right? Any map should do this because things are always related. So there should be a morphism in SAT from the carrier of P, which is forget P into X. Okay, so if I have such an F, then I can make a morphism, use the F, and then here to take a proof which says that X is less than Y and produce a proof of true, right? I think I can do that.
Are you going to do set and monoid, or is that the homework?
That's the homework. Right. And again, you could show that because we just use the underlying function here, right? You could also go the other way. So again, we seem to have this flip situation where, but this time we have a forget on the left and a chaotic on the right, right? So sometimes the interesting thing is happening on the right, sometimes the interesting thing is happening on the left. Yeah. Right, so we did the floors and ceilings. So what is the common pattern? Well, the common pattern is called an adjunction. So let's go and look at what an adjunction is. So here we have two functors f and g. And one is going from C to D, the other one is going from D to C. And we are saying exactly that if you have a morphism from f of x to b, so that's an f on the left, then you can flip it over to a g on the right and vice versa, right? If you have a g on the right, then you can flip it over to an f on the left. And these two ways to do it should be inverse of each other. So if I first flip it to the right and then flip it left again, I should get back to where I started, right? And vice versa. So that's exactly the pattern we've been seeing in these different situations, right? You can flip one functor back and forth. So the f is called the left adjoint, and the g is called the right adjoint, because the f is here on the left, right? And this is sometimes written f dash v g, so a little reverse turnstile. So we defined categories to have a set of morphisms. Yeah.
Yes, we're cheating slightly.
Yeah. Right. So this here is an isomorphism in the category of sets, right? Between this set and this set. So it's a projection. Yeah. Yeah. But then you see that we have to do this for every x and for every b, right? So we might remember that whenever we do something for every x and for every b, we would like this to be natural in some sense, right? In the sense that it shouldn't matter if we first use this 2 transformation to flip the f over, and then we realize, well, I want to change the x to some x prime by some functorial action. In this case, it's the functorial action of Hom itself, which is going to be composition. Or if I first use the f map and then transform, right? So that's what this the last field here which says that the 2 is natural, and because to and from are isomorphisms, that means that from is also going to be natural. You can prove that if you assume, and vice versa. But let's see if we can understand what this 2 natural is saying.
You say you get from
Yeah. Yeah, so here I define from natural, which is using the solver, and it's using 2 natural here in the middle, right? But okay, so what is this 2 natural saying? I think it's board time again. We have a way to turn a hom, I don't have it anymore, a hom f of x b into a hom x g of b, right? So here on the whiteboard, I'm not writing out the act. I'm letting you fill in the act. So that's what the 2 was saying, right? But then if I now, instead of an x here, I have an x prime, and instead of the b, I have a b prime, then I could also do a 2 down here, right? Because I can do it for every x and x prime. So this is x prime. This is g of b prime. So now, if I had a function f from b to b prime, then I can compose with that at the end to go from anything that ends up in a b can then end up in a b prime, right?
you are saying that rather than
Yeah, and if I had a morphism G, which
I
goes
think
from
you should call F and G by exactly the opposite name.
right, okay, yeah, so the F, yeah, you're right. So if I have a morphism G from B to B prime, and I have an F from X prime to X, then I can do F of the action of F on F goes from F of X, from F of X prime to F of X. So I can start by doing that to turn a morphism that starts here into a morphism that starts here.
You should also remove that misleading stray black mark that might be mistaken for a prime.
That one. So all in all, I can now go.
It's a bit glary, that's the trouble.
Yeah, right. So hopefully you'll remember if you. So if I start here with a morphism from f of x to b, and I want to make a morphism from f of x prime to b prime, well, then I can first do f of f. That's going to take me from f of x prime to f of x. Then I can actually do the morphism I have up here, right? So this is lambda h. This is h. So that takes me to b, and then I can compose with g, and that's going to get me to b prime. So I do end up with a morphism from f of x prime to b prime. So this is the home functor in both components. Yeah. Yeah. And I can do kind of the same thing over here, right? So if I start in x prime, then I can first use f to go to x. And then I can use the thing I've been started with up here, if I say lambda h again. So I use h to go to g of b. And then I can use g of little g to go from g of b to g of b prime. So that gives me a way to get from here to here and from here to here. And the naturality of 2 says exactly that it doesn't matter if you go around this way or if you go down this way. So it's another naturality square. Right.
You're in the way of the camera. You do
Right.
that from the other side. Yes.
Right. Yeah. Okay, but it's only 2 this ways in this diagram, so you can.
Yes.
F of G identity that gives you.
Right. Yeah. So then, so there's some useful common situations where you take one of these to be the identity, and then this simplifies a little bit, right? Because then this just becomes h and then g is this, right? So and the f disappears on this side and so on as well, right? So I think in the end of this file, I've given you some of the special cases because they're often useful. Yes, so I think, yes, special cases here.
Not very insightful.
The proofs are not very insightful, right? But the things that are not insightful can still be useful, you know. Okay, so let's see if the thing we have actually fits into this framework. So we claim we had this idea of maps out of the smallest order into forgetful things were really easy. So let's see. What do we need to do in order to actually turn this into an adjunction? Well, we have to give the maps to and from. We have to prove that they are inverse, and we have to show that it's natural, right? So the maps to and the map to. What is this saying? It's saying that if you have a monotone map from the smallest order, you should get a function. That was the thing we called morphisms out of smallest, all of them. And the other way, so that if you have a function, then you should get a monotone map. That's the one we just called this, right? Okay, and now we can actually show that they are inverses. So we are given an h, which is starting on one side, and then we are applying to and then from, and we want to end up at the same h.
You remember how to check that monotone maps are equal?
Right, we had a thing for this. So
And
it
they're
says
equal
that,
if the underlying functions are equal.
yeah, and
Which is
what does it mean for the underlying
Extremely-
functions to be equal? Well, that's reassuring, right? And the other way around, I think, is even easier.
So,
Because here we're already applying underlying function on the outside, right? So, this is roughly. Okay, and then finally we have to check this slightly scary naturality diagram.
which we
So we get an F and a G, which I even named the same here. That's reassuring. And
then
again, we are
shock
lucky.
horror.
So again, I think we had this pattern a few times, right? The interesting thing is coming up with the maps that actually transform data into other data. And then when you are in the business of constructing an adjunction, then these are hopefully easy things to verify, right? When you're in the action of using an adjunction, then these can be very, very useful to you. Right? But most of the time, the creativity is in the to and the from, right? Right, Connor, do you want to try and see if we were right about the chaotic thing, maybe?
I could give it a go.
For a change.
Remember the names of the things.
It's almost easier to do it again.
Is it the morphisms?
Into chaotic.
Was there? Do we only go one way?
I think we only did one way, so.
Maybe I'll do them again. Just out of locality. Right. So what have we got? We've got a function f. We need to make a monotone map. Yep, what happened there? What? Okay, so let's see. I'm obliged to construct a function, but I've got a very good candidate for that function. And I'm obliged to show that it's monotone, but it's extremely easy to be monotone when you're targeting the chaotic order. So you can see that that's just a function into a trivially inhabited type. I think Agda can guess what that function ought to be without me really bothering to answer it.
Right, why is that? It's because it's a function, so it better start with a lambda. So it's going to be a bunch of lambdas, and then in the end you need to give a body which is in the unit type, but there's only one element in unit type. So.
Right. Now I've got a monotone map, and I need to extract a function. I think I can just do that with fun. Okay. So let us see what we have here. There's going to be some H, some other H. Just check all of these bits and pieces. Okay, good. So that one was easy. I mean, all we're doing is packing and unpacking the function. So we should expect something vaguely sensible to happen. Okay, speak, monotone, map, something. Cool. Right, and I'm going to get an F and a G. And then I'm going to have a look at this. And what do I need here? I am comparing.
You're talking about compositions in pre-order, so you are comparing monotone maps, right?
Yes. So what needs to happen here? Okay, compositions in pre-order. So I need to use extensionality, I suspect. Well, I've got lambdas.
Oh, yeah.
So
Yeah, because we are comparing the function that takes an h up here and sends it this way down here or on that way down there, right? But it's for every h, which was called.
right, now I'm comparing monotone maps. These things are the things on both sides of my goal are monotone. And now I can see all of the octopus in my way. That's a win. Thank goodness for that.
Right. So you could say, okay, there's not much happening here, right? I mean, it's just raffle. What's the big deal? But I think one thing that's worth philosophizing about is the fact that forget is very, very simple, right? It's the most simple thing you could imagine. It's just throwing away some things. But it suggests to us to consider this chaotic pre-order as an interesting thing, right? We didn't just come up with that out of nowhere. We said, okay, we started with a forgetful thing. It went from pre-orders to sets, and we thought, okay, is there a way to go the other way that plays nicely somehow? So in some sense, the really simple and humble forget contains the seeds of the chaotic pre-order in it. And so it's often a good way to come up with interesting structures. Is you have something boring going one way and you think, is there a good way to go the other way? Right? And you know that you're onto something good if it actually forms an adjunction, so it plays nicely. So I think we can look at one more example of this, where again, let's take something really simple. I'm going to explain what it is in a moment and see if there's something interesting going the other way. Right? So the first thing I want to do is I want to say that, well, if I have two categories, then I can make a new category where the objects are pairs of the original category. And why do I want to do that? Because I want to consider functors of more than one argument, for example. Right? So that would be a functor from a pair category to something else. So let's see if we can do this. So I said that the objects here should be.
We're doing it now. I mean,
Yeah,
sorry.
so this category here, of course, is our own definition of category. Okay. It's not from the standard library or anything like this, because
so you don't use pairs.
No, there's no need. Right? So here I'm saying that an object in my new category should be an object of C together with an object of D. That was the idea I had. Right? I want to have functors that take two arguments, so I'm just making a category that packages this up as one argument. Right? And what should be a morphism between two of these things? So I get an object X and a Y, and I I get an object x prime and a y prime. So that's an object in my pair category. This is an object in my pair category. And now I have to say what should be a morphism from here to here, right? I'm defining it. And it seems natural to me that it, again, should be a pair of morphisms, one from x to x prime and one from y to y prime. Right?
Yeah, so we're just working, doing C things and D things separately, but in lockstep.
Yeah. You see, there's no interaction between the C and D things, right? A morphism in C and a morphism in G, and they never do anything to each other. Okay, then I should have an identity. But I have an identity in, right, let me actually, so this is,
This causes
yes. So here I want an identity on x, y, say. So that means I should have a morphism in C from x to x and a morphism in D from y to y, right? And the lambda here is because the Cartesian product in set gets desugared to a sigma, which doesn't actually depend. Second component doesn't actually depend on it. So this is something comma something. And then here I want this, so that's the identity in C, right? It fits here. And this is the identity in D. And similarly, if I have a composition of two things, I'm just going to do things component by component. So if I compose in C f and f prime, that gives me what I want. And if I compose in D g and g prime, that gives me what I want. Right. So it's perhaps not so surprising. I'm just doing things in parallel, like Connor said. Right. And now to prove associativity, well, that means that I need to show that this pair is equal to this pair, right? But I could do that by showing that they are component-wise equal, I hope. So if I do a Kong, and so a Kong lets me do this for one argument functions, but the pair here takes two arguments, right? So I'm going to use a Kong 2 of this thing, and then I have to give two things. Now, it's maybe not so easy to see, but if you think about how we define things, I hope you agree with me that associativity in C should be exactly what we need in order to deal with this first component, right? And similarly, associativity in D here. Right? Okay, and there's going to be the same thing going on with the identities, right? Right, so now I have my category where I can package two things up into one. And now I would like to think of a boring thing I can do with this category. So a boring functor. And I guess there are two really boring functors. That would be the projections that go this way, right? But I could also think of a boring functor going this way, which is the one that takes an object in C and duplicates it. So the diagonal functor, because it sends x to x comma x. So if you imagine this as a graph, it would be a straight line, right? So diagonal. So let's see if I can do this. So I said that I get an object x. I have to make a pair of objects. I'm going to say x comma x. If I get a function f, then now I need a pair of morphisms from xy to xy, so I'm going to duplicate my f again. And this is going to preserve identities, and it's going to preserve composition, because it's just doing things in each component, right? So that's my boring functor, and now I can think is there a way to go the other way in an interesting way? And it might not be the case for an arbitrary category C, but let's just think about the category of sets for now. And let's see, so we could start here from the adjunction, or we could start with the creativity. So in order to make a functor from pairs of sets into sets, then on objects, that means that we are given a pair of an x and a y, and now we have to somehow combine these to make one set, right? And if I want the adjunction to be this way, then that should mean that a morphism out of this thing into the diagonal should be the same thing as a morphism out of the original pair into just an x here, right? So I think you just have to play around a little bit. So I've already done my playing around because I named this in a particular way. So I'm going to try and make this x plus y, a disjunct union, right? Okay, and then you need this to be functorial. So I have this in the library already, probably.
Capital S.
Well, we need to unpack it a little bit. So we get a morphism in the category of pairs of sets. So that's a pair of morphisms, F and G. And now we have to make a morphism from this disjunct union to this disjunct union. And that's exactly what the thing in the library already does, right? So if I give it F and G, I think this should work. Okay, and then I should show that it's the identity. So I see that I want something to be equal to a lambda, so I'm going to use extensionality. So now I get given an x.
Yes, so we can see the thing on the left is doing some sort of case analysis. So we're going to have to make it unstuck.
Yeah. So I've realized I probably want to pattern match for my x, right? So I've used the pattern matching lambda. I don't think I need to do a recursive call, so pattern matching lambda should be fine. A very close is not needed. So let me pattern match on the x. It's either in inch 1 or inch 2. And in both cases, things are easy. So we made this sum function actually unstuck. Okay, and similarly, if we have a composition, it looks like it's going to be an x. Okay, I'm going to pattern match on my x very soon. Okay, and that looks good. And that looks good. Okay, so I have a functor. Now let's see if it actually forms an adjunction. So what does this say? So it says I have a function. Let me try and rename this a little bit. This x here is an x comma y, right? Okay, that's slightly better. So I'm given a function out of the either, the disjunct union, and I have to make two functions, one from x to b and one from y to b.
Yeah. Yes. So here, I mean, if we'd had slightly more time, and now I'm going to waste the time anyway, you might have thought, okay, what's going to give me with this x to b and y, this pair of functions from x to b and y to b? How could I kind of pack them up as a single thing? And it's like these are the two branches of some sort of case expression that'll give you a b whether you've got an x or a y. So that's where the either comes from.
So I get my f. And here I have to make a pair of two things. So if I have an x and I want to make a b, well, then I can package that x up as an ing1. I will turn it into this disjoint union, and then I can use the f to go to b, right? So f of ing1x. And similarly here, not allowed
Yes,
to use
don't
it.
you just wish that worked?
Here I can use ing2 instead, right? And what about going the other way? So here we are now given some h and some k. And we have to make a map out of the disjoint union. So let's just look at this x. What is the x? It's either an ing1 or an ing2. If it's an ing1, then I can use h to turn it into b, right? Is that right? Yes.
Mhm.
And if it's an ing2, then I can use k. So I just use whichever one I want depending on which component I'm in. Okay. And is this actually inverse to each other? So I get an h. So again, I'm trying to show that two functions are equal. So I'm going to do that with x. Okay, that's okay. And that's okay, right? And here is going to be the same thing. Right, except this is actually an f and a g, right? Okay, so this time we were lucky.
Yes.
These are, that's often the case, right? You're lucky in one way around, but not the other. And finally, for naturality, given an f and a g, the f itself is an f and an f prime. And
That's looking pretty solid.
that looks,
Done.
yeah. So again, naturality is not so hard, but okay, so we rushed that a little bit, but again, you could say that it's kind of amazing that the idea of the disjoint union of sets is arising from this boring diagonal functor, right? So that's a good exercise. Is there a way? So this is saying that functions out of the disjoint union are the same things as pairs of functions, right? Is there some way to combine x and y such that functions into this thing are pairs of functions? So that's something to think about. Okay, so the point of today was to see that you can get a lot of mileage out of just identifying structure. And we'll try to connect this to monads next week. I'm going to head off to Edinburgh now to go to the Agda implementers meeting. So we'll see what happens next week. But
Right.
I could always head back in the worst case. But the main developers of Agda are in Scotland this week.